All right, so last week we went over the basic definitions of what acids and bases were. And that's the main idea that you have to stick to when you're doing this chapter. Obviously, we will be doing some questions today, and we will be talking about chemical reactions of acids and bases. But the main thing you have to consider in any question on this topic is that you have to know the definition. Why? Why is knowing the definition important? Because the definition, as the name suggests, it defines what something does. So when you say acid gives H positive in water, then you have basically defined for all the reactions what acid is supposed to do. So the moment you see an acid, you're like, ye to H positive dega hi dega. And what is H positive? It's a proton, because hydrogen, it has one proton, one electron. You take that electron away, you're left with H positive. And what's that? That's just a proton. So acid is something that gives a proton away. But to do that, it needs some help from water. That is, basically it's called a dative bond, but we study that in A levels. For now, you just need to know that for something to be acidic, it has to be dissolved in water. So jab tak aap usko pani mein dissolve nahi karoge, you wouldn't be able to know whether it is an acid or not. Now, what happens when you put an acid in water? It loses H positive. It gives away the protons. But how do I know whether the protons are being lost or not? They're ridiculously small. So the way to do that is that we take indicators. We take universal indicator paper, we take pH paper, we take many other things like jo abhi humne us din discuss kiye the. We take phenolphthalein, litmus, methyl orange. We have 3 indicators here. We take any of those and we get some colors. And based on what those colors mean to us, or we look at the chart and that tells us what's happening. So if the color is red or orange or yellow, it tells me that it is acidic, which means it is giving proton. So indicators make things easier for us. We just need to put them there. We see a color change and we're like, okay, this is what's happening. Proton is being lost. So that is acid. Similarly, if you take phenolphthalein, it will give you a colorless solution. So you don't see a change. If you take litmus, you see a red color. If you take methyl orange, you also see a red color. And these red colors, or colorless for phenolphthalein, it represents that, wait a minute, this is what's happening. You are losing proton, that thing that was in there. Similarly, bases accept that proton. So it's the exact opposite of what acid is. Acid gives proton, base accepts proton. So any base that you have, what it's going to do is going to take H positive. Now, 2 ways of looking at that. Number 1, you look at the equation. So if you look at the equation and you see some change in there, okay, first of all, this thing had initially, maybe it had one hydrogen, now it has 2 hydrogens. So that shows that, okay, it has gained hydrogen ion. Okay, that's one. Or you can again take indicators. So if you take indicator like pH paper or universal indicator, then it is blue or violet if you have a base, and that tells me that any shade of blue in there, that represents it being a base. So it is taking proton. So it has more H positive, less H positive and more OH negative. Okay? Now there's a special category in there of alkalis. Alkalis are basically bases that give OH minus ion. So not only do they accept proton, they also do that by leaving OH negative. So OH negative wo lose kar deti hain, and that is how they become alkalis. They're all water soluble. Okay, so what that means is that not only are they accepting proton, they also have OH minus. So one way of looking at that is that if something has less H positive and more OH minus, then it is basic. If something has more H positive and less OH minus, it is acidic. And if something has the same amount of H positive as OH negative, then it is neutral. And that is what water is. Water, interestingly, is both acid and base. Kyun? Because water can give H positive, water can give OH negative. But the moment you join them together, you react them together, you're going to end up with H2O, which has 2H, 1 oxygen. So it is neutral. So the reason water is neutral is because it has the same amount of protons as well as hydroxide ions, same H positive and OH negative. So they cancel each other's effect, and that is why water is neutral. We give that a pH of 7. So 7 se niche, below 7, things are going to have more H positive, and above 7 things are going to have more OH negative, or they're going to accept H. So we took some examples here. We said that there is something called being strong acid and something being strong base. And what does that have to do? It simply means how many of those molecules actually do this. So we are saying that, okay, protons are being given off or protons are being accepted, but not every molecule in there is going to take part in that. So the closer you are to 7, the weaker that thing is. So if the pH is 7, then it's neutral. But if it is 8, it is very weak, basic. So it is on the basic side, but weak. Similarly, if it is 6, it's on the acidic side, but it's still weak. So that is how it goes. The more you converge towards 7, the weaker the ability to be acid or base becomes. The further you are from 7, the stronger that ability is. What exactly is that ability? It is that strong acid ionizes fully. So you take a strong acid would mean something that does to a greater extent. So if you have 1,000 molecules, all of them are going to lose H positive, then you say this is a strong acid. But you have 1,000 molecules and maybe only 100 of them or 50 of them lose H positive and the rest don't even take part in that, then you're like, okay, this is a weak acid. Similarly, we know that bases are supposed to accept H positive. So if you have 1,000 molecules again of base and they accept H positive, all of them, that shows it's a strong base. But if maybe a 50 or a handful of those actually do that, then you know this is a weak base. Examiner will ask you for pH sometimes. So you can just predict a pH. So for strong acids, take a value between 1 and 4. Don't say 4, 1, 2, or 3 is fine. For weak acid, take 4, 5, or 6. For neutral, it's 7 always. For weak base, you have 8, 9, or 10. And for strong base, you have 11 onwards, up to 14. Okay. And these are some examples that you definitely need to know. So this one is sulfuric acid. How do I know what the name is? So any acid will have H in it. So that's a given. Any acid must have an H in it. Now, these acids, they have 3 elements in there. There's hydrogen, there's sulfur, there's oxygen. So what we do is, to say if something is acid, we put IC at the end of the name. So this has sulfur in there, so it will be sulfuric. This has nitrogen in there, so it will be nitric. Similarly, these have just 2 elements in there. So we name both of them. So hydrochloric, again IC because it's an acid. This one is hydrofluoric or hydrogen fluoride, even if there's no water. This one is ethanoic, so it has OIC at the end of the name. And that is because it's an organic acid. So O because organic and IC because acid. So organic acids are written like this. They have this H at the end of it. That's going to be lost. But we will study that when we do organic chemistry. All right, so this was the extent of what we studied last time. We also talked about the idea of ionization. Ionization is when a molecule, for example, breaks down to make ions. And that's very interesting because you are having covalent bond and that covalent bond is being broken. But when it breaks, it forms ions. And that's quite unusual for us because we just studied ionic bond, we studied covalent bond. We never talked about things that have both of them. Turns out acids are covalent bonded molecules. So they have covalent bond in them. But the moment you put water in there, water does something called dative bond. And again, you don't need to go into the detail of that. So water does its magic. And then these things break down to form ions. Molecules breaking down, making ions. So hydrochloric acid, that's HCl. So it breaks down, gives H positive and chloride ion. Now, because it's giving one H positive for every molecule, we say that this is monoprotic. Monoprotic means that it's giving one proton. Now, examiner is never going to use this term. But some teachers, they prefer this. So that is why if you are going to school and they use this term, you should be familiar with it. That, okay, monoprotic, it means it's giving one proton. Similarly, HNO3, that is nitric acid. How do I know that? This is an acid. It has 3 elements. I take the middle one and I put the name there. So nitric, IC, because it's an acid. So nitric acid is going to break down and form hydrogen ions and nitrate ions. Now, an easy way of understanding where the ions are going to be is break it down like that. Similarly, take this one, break it down like that. This is hydrogen ions and sulfate ions. This is hydrogen ions and phosphate ions. So that is how they're going to break down and give us ions. This is hydrogen and fluoride. Obviously, this all depends or hinges on the fact that you know the 6 ions that we talked about. So if you do not remember, those 6 ions were sulfate, nitrate, hydroxide, phosphate, ammonium, and carbonate, of course. So these are the 6 ions that you need to know. So every time you see them, you should be able to figure out that, all right, these are the ones that I have here. Okay. So 6 ions, all of these ions have covalent bonding in them. So remember that if you, for example, in the MCQs, they can ask you that, all right, which of these substances has covalent and ionic bonding in them? So that's simple. Anything that has these, because for example, you have sodium hydroxide. It has hydroxide, which has covalent bond in it, but it also has sodium, which is going to make that is going to make ionic bond. Similarly, sodium carbonate, potassium sulfate, manganese nitrate, iron nitrate, iron 3 nitrate, iron 2 phosphate, all of these things, they are all going to have covalent as well as ionic bond. And that is because these ions, they are molecular ions. So these are the 6 molecular ions that you need to remember. Okay. And these molecular ions have covalent bonding in them. Some teachers, they also prefer the term polyatomic ions, but I just think that that's a very convoluted term. But again, everybody has their own preferences. So molecular ions or polyatomic ions, they are basically ions that have covalent bonding in them, but when they react, they form ionic bond. So if something has these ions, it's going to have both covalent and ionic bond, provided that the other thing is obviously ion. All right, so that was what we did last time, and I hope everybody is now familiar with this. Is there any question? If you have any question, feel free to unmute yourself and ask. We have a few new students here. Any questions here? Anything you did not understand?
No, sir.
All right, great. All right, so now let's see how acids take part in the reaction. Like, what are the reactions of acids? Okay, so that is, again, you need to refer back to the definition every time you see something like this. Another important thing to remember in this kind of chapter is the reactivity series, which is also sometimes called electrochemical series. So reactivity series is simple. You look at the periodic table and you're like, okay, which element is going to react faster than the other? So we have group 1, group 2, group 3. That's what I'm going to do now. Now in group 1, I'm going to talk about these two, then these two here, and then I have aluminum here. These are the 5 elements I'm interested in. And I want to know which one's more reactive, which one's less reactive. Now for metals, we know that the lower you are, the bigger you are. Because as you go down the periodic table, you're getting more and more shells. This is even more evident from the fact that this is period number 1, which means it has just 1 shell. This is period 2, it has 2 shells. So the more shells you have, the bigger the atom. Okay. Secondly, we know that metals always lose electrons. Okay. So that means the bigger the atom, the easier to lose electron, because a bigger atom will have an electron that will be much further from the nucleus. So it's going to be attracted much less. So let's compare potassium, sodium, calcium, magnesium, and aluminum. So now what have we established? We have established that when it comes to size, potassium is bigger, sodium is smaller in group 1. In group 2, calcium is bigger, magnesium is smaller. So that is the thing. Calcium is bigger, potassium is bigger. Okay, second thing. Calcium and magnesium are in group 2, so they're going to lose 2 electrons. So they're both going to lose 2 electrons, getting a positive 2 charge. These are both in group 1. They're going to lose and get plus 1 charge. And this one is in group 3, so it's going to get plus 3 charge. Okay, so potassium is bigger and needs 1 electron that it has to lose. Sodium is not that big, but it has just 1 electron to lose. So that shows that potassium and sodium will both be more reactive than everything else. Why? Because they just need one electron. The others have 2 or 3 electrons that they need to get rid of. But potassium and sodium just have one. So that means they are going to be much more reactive than everything else. All right, provided. Then potassium is the bigger one, so it's going to lose that electron much easily. So potassium is the most reactive. Between potassium and sodium, potassium is the most reactive. Why? Because it is bigger and they both need to lose one electron. Between calcium and magnesium, calcium is bigger and needs to lose 2 electrons, and magnesium is smaller and needs to lose 2 electrons. So calcium will be more reactive. Why? Because it's easier to lose electrons that are further away in a bigger atom. So calcium is more reactive, magnesium is less reactive. And obviously that leaves aluminium, and aluminium is down at the bottom because aluminium has to lose the highest number of electrons in there. All right, so that kind of reasoning works only up till this point because we haven't studied electronic structure in more detail. So when you go into A levels, you will do that. But for now, this is the explanation that you're supposed to know. Okay, what happens after this? What about the other elements? Like, what about transition metals? So in transition metal, there are a couple of factors that we don't need to get into for now. We just need to remember that this is zinc, then there's iron, then there's hydrogen, then there's copper. So these 4 we need to remember in that order. Now, of course, sometimes in the exam, they will ask you questions about tin, or they'll ask you questions about lead. They used to, they don't do anymore because of certain reasons. Or they can even ask you about silver. So for that, you just need to remember that they will tell you which reaction happens faster, which reaction happens slower. And what you have to remember here is that reactivity decreases down the series. Okay, so the lower you are, the less reactive you are. Why is this relevant to this chapter? Because these are all going to form positive ions. And there is one positive ion in particular that we are studying right now. So hydrogen ion is very relevant to acids and bases. All right, so what does this tell me? The reactivity series combined with the idea that reactivity decreases down the group. So I can say that copper is less reactive than hydrogen, right? Because that's what the reactivity principle is. Now, it also tells me that everything else in there, potassium, sodium, calcium, magnesium, aluminum, all the way to iron, anything that is above hydrogen, it is more reactive than hydrogen. Why is that important? Because if you have anything that is less reactive, a more reactive thing can displace it. This is called displacement principle, that a more reactive thing displaces a less reactive thing. Okay, fair enough. A more reactive thing takes the less reactive thing, brings it out of the molecule of the ion or whatever you have and takes its place. All right, fair enough. Let's see how these metals will react with acids. So let's suppose I take a very reactive element like sodium and I put it in HCl. Now the comparison here is not between anything and chloride, because chloride ion is still there. It is chloride negative ion. This is solid sodium. So sodium has nothing to do with chloride, but everything to do with H positive, because when sodium looks at HCl, sodium sees a positive ion and a negative ion. And sodium is like, wait a minute, this H positive, I can take its place because sodium is less reactive. You can see that this is high up in the reactivity series and hydrogen is there. And ions are more stable. So sodium loves to become sodium ion. And there is an opportunity here. Hydrogen ion can be converted back to hydrogen gas. Why? Because sodium is going to lose electrons and hydrogen is going to gain. Why? Because hydrogen is less reactive. So sodium is going to give its electrons to hydrogen and become sodium ion. And that will react with chloride to make sodium chloride. So all that has happened is that sodium has replaced H. Where does H go? H takes the electrons, becomes hydrogen atom. Another hydrogen atom comes in, they become hydrogen molecule, and you get this. And this is all dissolved in water. So basically what happens is that sodium, because it's more reactive, it can displace hydrogen ion, and that is why the reaction occurs. Now, if I had something that was not as reactive as sodium, but still more reactive than hydrogen, and put it there, same thing will follow. Zinc can still replace hydrogen, but not as rapidly as sodium can. So zinc simply comes in there, displaces this hydrogen, and you have zinc chloride. The formula is different from NaCl because zinc has +2 charge. How do I know that? I have to remember that. Okay, in O levels we have, or IGCSE, we have to remember that zinc is +2, and it is always +2. It is not a transition metal or a typical transition metal. And then we get hydrogen gas that's being given out. All right, so usually in the exam, they ask you for ionic equation. What exactly is ionic equation? You just show anything that changes chemically. You don't show things that do not change. So for example, if I look at the first equation, I have sodium solid. So sodium is a solid. And I have H positive ion, which is aqueous, okay? And I'm separating everything. And chloride ion, which is also aqueous. All right. On this side, I have sodium ion, chloride ion, both of them aqueous, and hydrogen gas. By the way, I have not balanced any of these equations yet. Okay. If you look at sodium, sodium is sodium atom here, and here it is sodium ion. So there is a chemical change. If you look at hydrogen, it is hydrogen ion here. It's hydrogen gas here, H2 molecule. So again, some chemical change has happened. But chloride is still chloride on the other side. It has not shown any change chemically. So we cancel this out because it's not showing any chemical change. So the ionic equation only shows chemical change, and that's what we have here. This becomes sodium ion, and that becomes hydrogen gas. And now you can balance this out. You'll have 2 here, and to replace those 2, you will need 2 sodium, and that makes 2 sodium ions. So taking that idea, go on and make the ionic equation for the second equation here, this one. Go on. So the first thing you have to know is that only aqueous things are going to be ionized, okay? That's a hint that you have. So zinc over here is not aqueous. We'll write it just like that, Zn. There you go. No charges, nothing, because it's solid. Then HCl is aqueous. So we put H positive and chloride negative because they are going to be separated by water. Then we have ZnCl2, which is again zinc and chloride ions, and they're going to be separated by water again. So this is zinc +2 and chloride, and there are 2 of them, sure. And then there's hydrogen, which is again gas. It does not ionize. It does not have any ions in there. So, all right, so let's see. Zinc has changed to zinc ion. So there's a chemical change, clearly. Hydrogen ions have made hydrogen gas. So there's again a chemical change. But chloride is still chloride. So it cancels out. So you're left with Zn plus H positive makes Zn2 positive plus H2. And because this is 2 hydrogen, you're going to balance it out by putting 2 here. And that's the ionic equation that you're going to get for metal displacing acid. Now, a common question that the examiner also asks you is about the observations. What do you see? What can you measure? What can you infer from this equation? Let's see. So zinc is a solid here, but zinc is not a solid here. It's aqueous. So what does that show? It shows that solid dissolves because it's breaking down and forming ions. Second, you have a gas coming out. You didn't have any gas in the beginning. So that shows bubbles coming out. So bubbles seen. Sometimes we also write it as effervescence. All right. Similarly, these are the observations that you can see, but there are some more deeper observation that you can actually make by measuring something. So for example, if I look over here, this thing had H positive on the left side. So before the reaction, there were lots of H positive ions. After the reaction, there is no H positive ion. When you have H positive ion, that thing is acidic. When you don't have it, it's not acidic. So in the beginning, you had H positive ions, but at the end, you do not. So then you can see that acidity decreases, or in other words, pH increases. Now, that's not something that you can see and infer. You have to actually make some measurements. All right. And lastly, if you measure temperature, you will see that this is mostly exothermic reaction. We have already talked about exothermic. Exothermic means it's giving heat out. All right. So that's exothermic. So that's how this ionic equation, or even this equation, tells us what reaction is happening and what you will actually see if you were to do this in the lab. So if you were to do this in the lab, what will you do? You'll take HCl. Usually we take, when you are trying to mix two things together, we take conical flask. So conical flask looks something like this. Okay. You take that and you put the acid in there. Okay. Now you're going to put solid zinc in there. So zinc solid pieces. Why am I using this conical flask? Because it's easier to swirl this. So I hold it from the neck. This is the neck. And I swirl it around, and that allows me to mix this solid very well with the HCl without spilling all of this all over the place and all that. Okay. So that's why using this is a really advisable thing to do in the lab. So we take this thing, we take the solid, we mix it together. We are going to get some bubbles of hydrogen gas. You can always test hydrogen gas. What do? You take hydrogen gas. If you do not know that it's hydrogen or not, doesn't matter. You take a burning splint and you put it in front of the bubbles. If it is hydrogen, it's going to give you a pop sound. If it's not hydrogen, it will do something else, or maybe nothing at all. But if it is hydrogen, that's a positive test. It confirms whether there is hydrogen or not. It will give you a pop sound. If you don't get a pop sound, you don't get hydrogen. Why does hydrogen give you a pop sound? Because hydrogen by nature is explosive. Highly exothermic reaction happening in a very short amount of time. So it kind of explodes, and that is the sound that you see. That you hear, I mean. Okay. So that was the reaction of solid metal with acid. But the thing that was common between sodium and zinc was that both of them are more reactive than hydrogen. Sure, sodium will react faster, zinc will react slower, but they're both more reactive than hydrogen. What would happen if I took copper and I put that in HCl? I'm taking HCl as just an example, it could be any acid. Actually, nothing will happen as long as I have dilute HCl. And all the questions that you get in the exam, they're usually about dilute acids. If I get a concentrated acid, it will react differently. It will take part in the reaction. Copper will do something, but we don't have to go into the detail of that because it's not required in our syllabus. Okay, so just remember that if you have concentrated acid, copper will react. I'm not talking about silver, I'm not talking about gold because they do not react even with those. But if you have dilute solution of an acid, then copper will not react because it is less reactive. So you'll just see copper, pink solid, just being there, not doing anything. Okay, so that was when you took metal and you added it to acid. What if you don't take metal, but instead you take an alkali and you put that in acid? So what happens? Now, displacement principle won't help us here because you already have ions. Displacement principle helps when you have one thing that is ionic and one thing that is not. Here, because you already have ions, they're simply going to mix together and make the best bond that they can. And that's what they do. They form salt and water. I'll briefly show you how. So let's suppose we take the example of sodium hydroxide and we react it with HCl. What should happen? What should happen is the moment I dissolve these in water, I should get lots of ions. Which ions in particular? Sodium ion, hydroxide ion. Both of these, because this is an alkali that have dissolved in water. And then hydrogen ion and chloride. Okay, so I will get sodium ion, hydroxide ion, hydrogen ion, and chloride ion. Now, as you can see here, this hydrogen ion is being given off by an acid. And this is an alkali. This is a base. it wants to get H positive. So that's exactly what it does. This hydroxide will bond with this hydrogen ion and you will get water. And once that is done, sodium and chloride are the only ones that are left over. So they bond together. But remember, these, as long as there's water, they will not bond together to make solid. They will still remain aqueous because they're still suspended in that water. Okay. So what happens to the ions in there? So hydrogen ion and hydroxide ion, they're both reacting together and they're forming water, which is water. It's not ionic compound anymore. It's molecular. And then you have sodium ions, which are still floating around, chloride ions, which are still floating around. So let's cancel things that do not show any chemical change. So sodium ion does not show any chemical change. It cancels out. Chloride ion does not show any chemical change. It cancels out. So you're left with what? H positive, OH negative makes water. And this is called equation for neutralization. In fact, in the MCQs or even in the question paper 2, sometimes paper 4 for IGCSE people, what they do is they just ask you, write the equation for neutralization of some salt, neutralization of some acid and some base. And the important thing to remember here is that neutralization does not depend on what the reactants are. Neutralization always occurs if you have an acid and an alkali. That's it. It does not depend which acid or which alkali. It does not matter because you're always going to get H positive and OH negative. All right. So that is why every time they ask you, what is the equation for neutralization? It's this one, H positive and OH negative. If they ask you to pick one of these in the options, pick this one because that is always neutralization. Everything else can be different, but this one will always be the same. Now, alkali can be different. The choice of acid can be different. The salt form will be different. But the equation for neutralization will always be H positive from acid reacting with OH negative from alkali, making water. In the beginning, I asked you to remember the definition. Let's see how definition is relevant here. Look at the negative ion. Over here, I have chloride. Over here, I have chloride. On the left side, chloride has hydrogen. On the right side, chloride does not have hydrogen. That means it has given hydrogen out. It has given it away. That makes it acid. Similarly, look over here. OH has just one H. It does not have H positive here. On this side, it does. What does that show? Over here, it had one hydrogen. Over here, it has two. What does this show? It shows that it's an alkali. It has accepted H positive. Okay. And that is how we know this is base, this is alkali. So from the equation, you can easily infer that something is acid, something is base, because you can just count how many hydrogen it has in the beginning and at the end. Okay, so these are the two main reactions of acids and bases. What happens is you take acid and you add it to metal, and metal will displace the hydrogen ion in there if it can. If it cannot, then obviously the reaction will not happen and they'll just stay there. And second is, if you have an alkali and it's reacting with acid, it will form salt and water. That's it. What if you don't have an alkali, but you have a different base? So bases come in different categories. Like you can have carbonates with metal. So metal carbonate is base. Metal oxide is base. And obviously metal hydroxide is also base, just like we've seen in alkalis. What happens there? If you put these two things with the acid, they're going to do the same thing. They're going to form salt, they're going to form water. But this carbonate will do something else. It will give off carbon dioxide. And that is what carbonates do. They give away carbon dioxide whenever they react. Unless you are reacting them with some other bases or something like that. So remember that whenever carbonate reacts with acid, it gives carbon dioxide gas. So you will, just like in hydrogen, you will see effervescence. You will see bubbles every time a gas is coming out. With metal oxide, nothing like that happens. So salt plus water, that is what you get. So important thing to remember here is that carbonate will give off carbon dioxide. Another important thing is that most of the time, these are not very reactive. So unless it's group 1, by the way. So if it is group 2 oxide or group 2 carbonate or group 3 hydroxide or something like that, we usually will have to heat them up. It's not required, but if you heat it, they get kinetic energy, they collide more, they react faster. So all of that can help you complete the reaction. Okay, so that's what they do. I will be sharing a worksheet with you to solve today. We will be reviewing more reactions of acids and bases tomorrow, and we will also solve some questions from past week tomorrow. All right.
Let's go. Yo, I'm like an addict, do I gotta have it. I ain't even playing, got a really bad habit. If it moves